I just want to thank Sahil Siddiq here, our PhD student, who will actually co-teach this tutorial with me. So the way we have organized this is, I'm going to do the first day, and then Sahil will kind of take over and do the next 2 days, and I'll sit in the audience and help him as needed. Today the roles are reversed. I'll do the teaching. He will help us needed. So the thing is, the motivation for us comes from the fact that there is a lot of work nowadays in generative models, in deep generative models, variational autoencoders, GANs, and so on and so forth. But there are many tasks that many of these deep learning models cannot quite do, that classic AI does very well, right? I mean, classic probabilistic machine learning can do very well. So what we are trying to do is, we are trying to see if we can bring them together. Can we get inspired by I don't know, the deep models to build better probabilistic models, or can we get inspired by probabilistic models to improve deep models, querying and stuff. So what the way I am going to do this tutorial is kind of give you the background of these models today, and then Sahil will have a collab style working tomorrow, right. So maybe you want to get the list of registrations and send them the collab notebook so they can all join tomorrow. So for tomorrow it's going to be very hands on, okay. So we'll give you some data, you will work with us, run it, and then see the results and so on. Today is more tutorialish, where I am teaching, and we are going from this, okay. So the most important thing is, be it my classes, my lectures, my workshops, my tutorials, my request always is to interrupt and ask questions, okay, at any point, because the thing that I always think is, there is really no incorrect question, it's just difference in model. I have a different model of the world, I have how it works, how I am explaining in my head. You have a completely different interpretation of what I am saying. So asking questions will bring both of us to meet in the middle. So feel free to interrupt, feel free to ask questions. I might just signal to wait till I make the point, but feel free to interrupt at any point, okay. So we are not going to do this like a formal talk where I speak for 45 minutes and then give you 5 minutes to ask questions. Just feel free to interrupt at any point, okay. So with that, once I get this moving, okay, there it is. So today, as I said, day one, we are going to look at probabilistic generative models, and specifically we are going to look at probabilistic models, Bayesian networks, Markov networks, and so on. Why do you need this, and what are the applications that we could do? What I am going to do is kind of explain to you what we do in the lab as we go, so you understand like how we have been working with these problems. Let me tell you this, when you work with healthcare, and we work a lot with healthcare, half of my funding comes from in US you have what is called National Institute of Health, essentially looking at healthcare problems, all the way from predicting heart attacks, diabetes, to very recently we have been working with actually even Government of India on using AI to improve outcomes in pregnancy. So how can we avoid adverse pregnancy outcomes, and very recently we even got an NIH grant on predicting injuries in children. How can we figure out if a child is admitted in an ER, an emergency room, can we avoid the child going into some sort of a trauma? Can we how can we help intervene early enough? So those are the applications. So to do that, we are going to use probabilistic graphical models, and then we will talk about inference and learning. Again, this is just a rough sketch. I am not married to this slide, so this is just a rough guide for us, okay. And the way I typically even do my teaching in classes is, I teach for like 35-40 minutes, give you a 2 to 3 minute break to get your phone thing out, and then we will come back, talk again, and then I think there is a break. I suggest that we take a break at 10:15 for about 20 to 25 minutes, and then we will continue the same way. Another 40 minutes, I will give you a 2 minute break, and then we will continue, okay. And tomorrow, try and follow the similar schedule, 40 minutes, give them a break, and then I will be there, of course. So we are going to start looking at the more interesting, more exciting recent work, because as you will see at the end of today, well, this is all beautiful, but if I am going to give you billions of images, day one does not scale, okay. Day one works beautifully if you have data from one hospital, if you have data about 10,000 patients, you have data about 15,000 women and their pregnancy, but then you suddenly say, I am going to give you 1.5 billion data points, right, it breaks. the day 1 break. So that's where day 2 comes, where we are going to show how can we do this idea called probabilistic circuits. And by the time we hopefully at the end of this day, you will see that the 4 here directly feeds to the 2 here. Okay, so the inference and learning in graphical models are used to inspire this idea of tractable generative models, and you will see that in day 2. And in day 3, I think that's supremely exciting, because that is where we are going to present the most recent work in this direction, including Sahil's own PhD thesis, another student from my lab's PhD thesis. He's got an excellent survey paper. Maybe we can also send that out once this day 3 is over. We have written a beautiful survey paper at a premier AI conference called ICHCAI this year. So we can, if you are interested, of course we can send you that paper, and of course at that end of day 3 we will invite you to join us and work with us on these exciting problems. Again, none of these are just by ourselves. There's a lot of work previously done. We offered a condensed version of this at COTS COMAD this year at Bangalore. Saurabh and Sahil were both present along with myself, and they actually did the whole workshop. And there's a lot of work by Guy Vandenbroek's group from UCLA, and that UCLA group has done the work on probabilistic circuits. They have been giving a lot of tutorials. Maybe we should have also included a thanks to Stuart Russell and Norwig's book and David Poole's book, because a lot of my work, particularly on first day, comes from Wenkeen Wang, the person who taught me Bayesian networks back in the day, along with those 2 books. And of course, special thanks to our 2 PhD students who could not be here, who would be great as well to present this tutorial, Saurabh and Atresh. So with that, we'll get started. So we're going to talk about the foundations of probabilistic generative models. Again, feel free to interrupt at any point if something is not clear. If you think I should slow down, if I'm not explaining something clearly, make sure you ask me. Okay. So I like what these guys have come up with, right? So Richard Feynman, whom you guys probably know very well, is a famous physicist and has written a lot of books. Particularly the books, his biography is a beautiful book, and it's one of my inspirations as well. And he says, what I cannot create, I do not understand. Okay, so if I, and we used to flip this quote back in 2002 and 3, what I cannot code, I cannot understand, right? So that's the thing that we tell students, code. If you code an algorithm, that's when you understand it. So his thinking was, what he cannot create, he cannot understand. And my students flipped that out, and he says, in generative models, what I understand, I can create. So if I understand the world, I can generate it. Okay, so that's the beauty of generative models. So what is a generative model, if you ask, right? So the whole point of generative models is that we can, if we understand how the world is evolving, you can create that in a simulator. So for instance, if I sit here and I observe how the traffic pattern moves from Gajendra circle to here, and I sit and do this for 10 days, and I've observed the entire traffic pattern, and I've got a model in my mind, then tomorrow morning I can just recreate this in a simulator. I can create an IIT driving simulator. How do you do that? By collecting data. But what is this data? This data is not just features with a label. This is a data that talks about how the world has evolved. So you are generating the entire thing. Okay, so that's why these are called generative models, in the sense that if you learn a good generative model, this is the beauty of generative models. If you learn a good generative model, you can throw the data. You don't need data once you have a good model, right? So that's the idea. Whereas with discriminative, you still have to keep updating the data as you keep going. Okay, so and what are these generative models, right? So I mean, this is not how I would start, but this is how they start. So I'm going to go with their story, right? So you have a generative model which is parameterized by some distributions. Okay, so again, we are in a probabilistic setting, so we're going to talk about probabilistic generative models. So you are in a generative model space where you have, depending on what parameters you use, you are going to get different models. Okay, it could be the same structure of the model, but the way you generate things may differ. So for instance, if I'm generating data in Madras, let's say, and in Chennai, and I'm saying I have to drive 2 kilometers at 8:30 in the morning, okay, your model might say it will take 15 minutes. okay, not fair, not bad. The same thing I do it in Dallas. 2 kilometers is about a mile and a quarter of a mile. You will probably end up doing that in 5 minutes. Okay, so you will see that that based on the parameters of your model, you are going to get different outputs. You'll get different instances of that model. So that's the idea. And what we get is we don't really quite understand this generative model, right? So if you believe in God, God has a model and they are generating data, so according to that model, right? Or if you believe in evolution, science, whatever, right? So evolution, okay, world creates model that way. And there is a stochastic model that has been created. Now the question is, this is a fundamental problem even in machine learning as such, right? I don't know this true generator. I do not know what exactly generates this data. What do I have? I have data. I have observations, but I don't know the generation process. Okay, what do I want? I want to build a distribution that is as close to the original distribution as possible. That's the goal. So to do that, what do you want? What do you want? You need some data. Well, not some data, you need good data. What does good data mean? A good data is representative of the problem at hand. If I am going to predict the pregnancy outcomes and I am only looking at white American women in a suburban city, right, like Dallas, and I have data only from white American women, that's not representative of anything. It's representative of that particular location. How can you generalize it? So you want to have good data, but what are you learning? In the end, what you are learning is an approximation of the true model. How good an approximation is depends on the problem at hand, depends on the data at hand. So machine learning, how many of you have looked at Tom Mitchell's book? If not, that's the first book you should read. Okay, machine learning is fundamentally ill-posed. What does that mean? Essentially, there is really the whole problem of machine learning is ill-posed in the sense that you are not given the perfect data to learn. Why? I give you 100,000 features, okay, and then I don't know 10,000 examples. Can you imagine the number of combinations? You are always fundamentally at a problem where you have less number of data points to more number of combinations of features and data points. So, but doing this in the context of generative model is even more difficult, because there I am just learning a distribution. Let us see if this works. So there I am in a classic machine learning, I am learning this. What is the probability of y given x? Okay. Here this y is the label and x is the set of features. Okay. It is a easier distribution. What I really need in a generative model is actually p of x and y, or y and x. It is commutative because it is a conjunction. Okay. Now this, as you know very well, is p of y given x times p of x. As you can see, learning a generative model is strictly harder than learning a discriminative model, unless I make assumptions. So you have to make some sort of assumptions on the prior distributions. Okay. So the point I am trying to make is that I don't know if this was the point you wanted to make with this slide, but essentially the problem of learning generative models is figuring out what is this distribution that I am going to learn that best approximates the true distribution based on the data that is being given to me. Make sense? Any questions? So this is the fundamental problem in machine learning, okay, and in probabilistic graphical models. I suddenly thought of the machine learning book. I wanted to say something about the machine learning book, but it will come to me. But yeah, so again, let us take a simple domain that I have in hand. Okay, the simple domain is that well, it is not quite simple, but it is a nice domain maybe. This is what we work with. Okay, so we are interested in mitigating our pregnancy outcomes. US is supposed to be a first world country, right? That is what they call themselves, first world country. I'm a US citizen, by the way, so I can say that now. And for that, 18% of every pregnancy, 18% of pregnancies have some complications, which is 1 in 5 women. Giving birth is the one thing that we should know very well, because we have done this for a few thousand years. So we should know how to give birth, but we have problem 1 in 5 births in the US. In India, it is actually 16%. It's not that in India is any better with all our holistic teaching and holistic practices. And this ranges completely differently, right? All the way from gestational diabetes, which is diabetes during pregnancy, to preterm birth, always a problem. Okay, you want to extend the child's stay inside the mother's womb as long as possible, right? 37 weeks is what you are expected to get to full term. And then there is other things like preeclampsia, fetal death, actually even maternal death, and in this case growth restrictions and stuff. So the question that we were asking is, can we look at the data from a small set of people, 10,000 women across 8 centers in the US. We had about 7K variables, and the goal is, can we somehow figure out how to mitigate adverse pregnancy outcomes. This word nulliparous means first time, first pregnancy. Okay, so it's not like they have been pregnant more often. Again, this is very crucial depending on race, age, and so on, right? And actually certain things even depend on gender. For instance, they say, oh, the mother cannot be too old to have a kid. You know what? Flash news. Even father cannot be too old when a kid is born, because the father's age is directly associated with the risk of developmental disorders in kids. Autism, right? Most important cause of autism is that the dad is older than 40. So the point I am trying to make is that we have not understood this space very well. One of the things that we are trying to do is, somehow can we use the data to learn something, so to understand the space of pregnancies. So here is the problem, right? So maybe one of you should ask, why is this not a classic machine learning problem? Very simple, because I am not interested in one outcome. I am not saying how can I minimize the neonatal death. Okay, that's one problem for which you can learn a classifier. But now I say, how can I minimize gestational diabetes? Oh, wait, I am going to train another classifier. Okay, go do it. Now I am going to say, what is the probability that somebody who has neonatal death, whose kid died during pregnancy, actually had gestational diabetes? Wait, I need to build another classifier. That's not going to work. What we want, on the other hand, is something that understands this whole pregnancy as a process and can learn to ask questions, learn to answer questions in that space. Let me give you some tidbits on this problem alone. I just want to tell you why this is a very important problem. The government of India has now an initiative called Garbini. Professor Himanshu Sinha here is leading it at IIT Madras. I am also working with them as well. I am working with the government of Brazil to improve pregnancy outcomes in a Brazilian population. Because of the fact that Portugal occupied Brazil, we now actually have Portuguese people also in our population. So I am working with the government of Portugal along with my collaborator to get some data on that group. And now very recently, Professor Milind Tambe and us, we are trying to look at an African population to see if we can improve the pregnancies there. And you see differences, very simple. South Asian women have a less risk of gestational diabetes. That is, they do not have as much high risk of gestational diabetes as an African American woman or a Chinese woman. Chinese is a classic example. But here is the problem. Most of the South Asian women who have gestational diabetes after pregnancy will continue to have diabetes, type 2 diabetes, for their life. Whereas Chinese women, it is like a switch. The moment the kid comes out, diabetes is gone. 99.9% of the Chinese women will go on to have normal life. That is not the case with South Asian women. So why is this happening? What is the effect of genetics on this? So to answer these questions, you want to build a more holistic model rather than just a simple deep learning classifier. Is the motivation clear? I am taking a lot of time to set the problem up, So, we are all on the same page. Any questions? Okay. Okay, so that's the idea. And again, we have to say, when I'm giving a talk like this, I want to put all our citations in here. So you see that we have done enough work in this area, this type of problem, to actually explain about this. Our goal is to kind of build this agent we call the Starling agent or statistical relational learning agent, which observes the population and then understands why the treatments are done the way they are done. So, for instance, let us say one woman comes in, she has some infection, when you are pregnant, typically they do not want to give antibiotics because that can cause some developmental issues in kids. So, particularly ADHD can be a side effect if you give antibiotics during pregnancy because the good bacteria is lost for the kids. But on the other hand, let us say the infection is serious enough, then you have to give the antibiotic because you want to save the mom and the kid first. So, the question is, in each of these cases the doctors are making a judgment call. They have the best intention in mind, they want to save lives, they want to solve the problem. So, they have the best intention and they want to solve this thing given these constraints, but they are not going to take the same one shoe fits all approach. So, each of us have a different treatment plan. Forget this particular problem, diabetes, right? I have diabetes, and I think I said that even yesterday in my talk. I have diabetes. And I have had 3-4 doctors now. Each of them have approached my diabetes in completely different way. The white American male doctor hit me with metformin like crazy, max dose of metformin. My blood sugar was like 6.4 and I had the maximum possible dose that a human could eat. And now I have a South Asian woman as the doctor. She is actually Tamilian, settled in US. And she is very calm. It's okay, you're doing okay, let's keep going. And I have a very low dose. When my blood sugar level now is higher than it was 8 years back. Why is this the case? Because each of them have their own preferences. But if I ask them, they are not going to give me the reason, but the system could ask them, wait, why did you give this dose to Sriraam? Let us say very simply, right, like 10 years back I had this knee injury. We went to the doctor. The doctor was talking for a few minutes and then he comes up with something. Let us say that he puts me on steroid. The system should be able to say, hey, Sriraam has diabetes, you are giving him steroid, it could pump his blood sugar up. Then the doctor should be able to say, no, I know that he has diabetes, but he is in acute pain. I have bumped up his metformin, or I've asked him to exercise more, whatever. I want to bring his pain and inflammation down. Or the doctor could say, thank you, that idiot was on his phone all the time. He did not even say that he has diabetes. So I'll start with Brufen, see if we can do that well, and then we'll come back to prednisone, the steroid that they typically give for injuries. So question I'm trying to, the problem I'm trying to pose is that each doctor based on each patient has a completely different treatment plan. But there is a generative model underlying in the whole thing. They are thinking about the whole process holistically when they are making decisions. And so we want to build these agents that can actually observe, ask the right questions, in this case saying, so why steroids is the question, and then the doctor could give a response back, and then the system could use that and say, okay, now I understand how we are going about this. So tomorrow a similar patient comes, I can have suggestions for you. But in the era of LLMs, this is my dream. In the era of LLMs, you want to be able to say something like, there is a new literature that came out that there is this particular drug that is more effective than prednisone. Because doctors get trained only once a year, if I understand this right, but research moves faster than that. How can we use the data that's been published to better inform doctors? That's our long-term vision, long-term goal, is to keep this much more hands-on. Okay, so what are we doing that is different? Because if you think about it, like I said, you are going to say in every one of this, in a classic machine learning, you are only learning P of y given x. Y is your label and x is the set of features. So in classic machine learning, you are learning probability of gestational diabetes given everything that you have, or probability of preterm birth and given all the observations. Maybe you do not know gestational diabetes, you do not know preterm birth, so both are hidden, both are not observed in the data. You are going to reason about them, right? But now I want to say something more complex. Given that the woman is at a high risk for gestational diabetes, what is the risk of preterm birth? You see the question? I think that based on your data, the data I am looking at, the women is a high risk of gestational diabetes. Whoa. The women is at a high risk of gestational diabetes. What is the risk of preterm birth? Now, if you do look at this problem, you have to use one as a feature in another. So, when I am doing this question, I am basically saying what is the probability of preterm birth given that gestational diabetes risk is high and all the other features. So, you see this becomes a new feature. So, should I train a new model? That is what you are expected to do, or train some approximations. You will make this slightly differently. You will make something like, oh, I am going to assume some independencies, and I have this from this is my classifier that I learned. This is the classifier that I learned, maybe your deep neural network, and then I am going to multiply this with probability of preterm birth given GDM. That is an assumption. It is an assumption about the independencies of these two. That is not true, or actually the independence of this given this, it is not true. These are called conditional dependencies, we will come to that later. They are not always true, but these are simplistic assumptions that you make to get things to work. Where do these assumptions work? When you have billions of data points. When you have billions of data points, there is a lot of assumptions that work. There is a reason why deep learning works beautifully. Why? Because all of us have sold our soul, or rather our phones, to Google, to Apple, to whoever, Facebook, to Instagram, wherever, right. We have given all the data to them, all your images are with them. It is there somewhere in the fine print, even the font size you can't read. The point is they have all the data, now they can do whatever they want to, and of course then you get good results. How many of you know MNIST data sets? I would be surprised if I see lesser hands than this. How many of you think it is actually valuable? Because of the fact that I asked, I am seeing only one hand, but most of you would, how many of you would still publish papers with that? My student. We need, why? Because the reviewer asks for MNIST. Why? It is a benchmark. What benchmark? You are pushing from 96.2 to 96.27, ooh, awesome. No, no, but that is how research evolves. The point I am trying to make is that with large amounts of data, all kinds of, pardon my French, but all kinds of shitty, crappy assumptions work. The moment you have small amount of data, large amounts of knowledge, those assumptions break, and that is where generative models are more powerful. Okay, they are more principled in doing this. Okay, so why do we need this? Again, because the questions keep changing. What is the probability that I can reach Gajendra circle from central in less than 30 minutes? You forgot to do the second one bullet. I filled it, but I forgot to send it back to you. So, this requires in some sense marginal inference. What does this mean? This is basically saying I do not know, time to Gajendra circle equals 30 given that origin is central. Okay. Except here is the problem, my data includes a lot of other things. Okay. It includes things like time of the day, traffic, routes, patterns, so on and so forth. You have everything in your data set, but I am only interested in this query. Maybe you can say, well, I am reaching at 8:30 in the morning. So, we could add that saying time is 8:30. So, what you do is you basically do what is called marginalization, which is you sum out everything that is not in, we call it evidence. Okay. So, this is the query, the question that you ask. Okay. This is the evidence, not this, but central is the evidence. Okay. So, what are the other things that are there? You will do what is called summing out. Those are not relevant, they are irrelevant to the question at hand. So, you can answer that very well. You can flip the question and ask, well, when is it most going to be congested? What is the worst time to take this road? Turns out that it is the same exact model that you need. The only thing is you will change what is called as argmax. You will find the instantiation that maximizes the probability of, I do not know, the time. Time is in this case, how do you pose it? Time is greater than some delta, given that the r is theta. Okay, and you can pose that, and you can actually have more things. You can say things like, what is the maximum congestion that I am going to take, given that I am going to take this route? When should I leave for Gajendra circle so that I reach Triplicane within 30 minutes, but I have to be in Triplicane by noon? So, you see the questions that you can pose. You can pose any kind of questions. There is only one model, which is the probability of the label and the features together in this case. So, you have this called marginals, and then you have map or maximum or posteriori. You can have marginal map, and so on. You have conditional queries, you have unconditional queries, you can answer any type of queries. Is this in line with what you are thinking? Okay. So, what are we doing? Essentially generative models, right. So, generative models, and this is a slide due to Tom Dietrich, I need to thank him for that one, can generate examples. So, you can, if you once you have the model, you can generate newer and newer examples, and it can compute it can complete feature vectors. So, for instance, I will give you something like, I do not know, let us just take one, height, BMI, A1C, blood sugar level, high blood pressure, HBP, low BP, in this case not the systolic and diastolic in this case, and then let us just do heart rate and so on. And you could say, well, this person has a height is medium height, BMI is medium, A1C is low, I do not know the values for this, I do not know the heart rate. So, what is the risk of heart attack? P of heart attack is what, given this, and you can answer that question, because these I do not care, this is there, it is a marginal query, okay. But the flip can also be done. I give you this data where this is marginal, medium, low, heart attack is false. Let us say, I do not know how to do this, let me check. Oh, eraser, good. Let us say that. Okay. So, I have this, I have heart rate, and let us say that I have heart attack. Now, heart attack is false. This person does not have a heart attack and has a medium height, medium weight, and low blood sugar. Now, I do not have the rest of the data. Can you fill in the data for me? Turns out, if you have a model, okay, which is parameterized by this, and then I have this yx, x is all this, y is the heart attack. Okay, I have this model. I can actually fill in the values for you. These are the most likely assignments of values to the variables. Okay, now I can say generate a new person. So, I can create a new positive example, completely new person. That is what you see, all these new fake videos, deep fakes, and so on. You can generate a new negative example, okay, and then you can basically say which of the model is most likely to generate it, and you can answer more deeper questions based on these. Make sense? Okay. So, with that, again we are going to see multiple ways of doing this. This is the easiest of the and the oldest one. This is from 90s to now. There is a lot of work in this direction on probabilistic graphical models. This is what I am going to focus on today for most part. Tomorrow we are going to do the species, and this is starting in my head 2004 to now. Okay, and then on Friday, Sahil will talk about, this is I think 15, right, or 16, 15, 14, 15, something like that. Last 10 years, there is some work in deep models on probabilistic models, and this we are going to see on Friday. So, in some sense, I am going to give, the two of us are going to walk you through the history of probabilistic generative models. Any questions? Okay, I think that's a good point to take your 2-minute break. Let's take the 2-minute break and then we'll continue again. Yeah. Yeah, Tom Michel, machine learning. If you're planning to go to US, buy the book here and then go. Because even 20 years back it was $120 in US, it was 250 rupees here. So my American friends used to tell me to buy the book from India and bring it there. So buy it here, it's worth it. The PDF is free. No, legally, not illegally. I cannot promote illegal things, but legally it is free. You can download. And actually, Tom Michel, who is my academic grandfather, he's my advisor's advisor. He was very keen on pushing all the chapters out, and he couldn't quite do that because of his busy schedule. Another book that I recommend is by Poole and Mackworth, David Poole and Mackworth. That's an AI book, but it has a good machine learning sections. I mean, it's a few chapters of machine learning. Okay, anything else? All right, let's take the 1-minute break. Yeah. Sorry, I can't hear you.
We have just an induction session in RBC WSAI. So is it okay, sir, like if we leave and if we have this all recordings?
That's fine. Yeah, that's okay. No problems. Yeah. It's always a proper choice of parameterizations, and that comes from data. And I claim against my students' liking that it also comes from domain knowledge. Good domain knowledge can influence the choice of the parameters. And these probabilistic graphical models, they have a good way of writing the generative knowledge rather than, let's say, a deep neural network or something.
So you were mentioning that there is a difference between having a lot of data and knowledge. You mentioned that.
Yeah.
So knowledge, as in you mean, so data is usually just features. So knowledge, do you also mean the interaction between those features?
Yeah. As A increases, B increases. As weight increases, risk of heart attack increases. As diabetes increases, risk of stroke increases. These kinds of knowledge are worth way more than an example. I mean, I think that's a completely different lecture. But essentially, if you think what a knowledge does, is as A increases, B increases, is going to define a polygon like this and say everything inside this is going to be a positive example. So you might actually have original positive examples like this and negative examples like this, right? Maybe these were not good choices, but let's see. Okay, and your positive examples could lie like this, right? And if I did not give you this piece of knowledge, if I'm going to learn a classifier, the classifier could have been this. But this knowledge essentially says no, this part is also a positive example. So the new classifier is probably going to be this. Sorry, the new classifier will probably be this, and that difference is what you get from knowledge versus data. Knowledge will always be good constraints. There's a lot of work in that direction. Knowledge based machine learning. Actually, one of the most beautiful papers is by John McCarthy. You know who McCarthy is? Anybody knows who McCarthy is? The father of AI in some sense. And he has this beautiful book called On Advice Taking Systems, paper from 1955, where he wants this domain knowledge to be incorporated in learning systems. So this is an idea that's not new. It's not Sriraam who's doing it. 70 years back, it was thought by McCarthy back in the day. So my claim is that what we are moving, this data is everything, is nonsense. Knowledge matters, because some of the observations that we had 20 years back, we don't get it anymore because the world has changed. But the knowledge exists. We should be able to use it in a more positive manner. Yeah.
This is more from a compliance point of view, imposing this or superimposing the probabilistic way of thinking on the generative models would make it more explanatory and more
Exactly.
interpretable?
It's more interpretable, it's more explainable, it's more interactive, because you can ask this question, what if I change this, what would be the effect? So it is, you can put these domain constraints, ethics constraints, safety constraints, explanation requirements on the model directly. So that's why we go for probabilistic machine learning.
Because as you said, the earlier expert systems, we had the advantage of
Doing that, and we lost that in these deep models. And so there are two branches of machine learning that are doing that. One is called as the neuro-symbolic system. The talk that I gave yesterday was like one of the instances of that. So the combination of a deep neural network with the symbolic representations used by expert systems back in 80s. The combination of those two is now they call it as neuro-symbolic learning. We used to call it statistical relational AI, but now it's neuro-symbolic learning. That's one way to do that. But even there, it's what Cynthia Rudin from Duke calls as, I have a black box model, and then you're trying to make it white box, and it's not going to work, right? If you want an interpretable model, learn an interpretable model, and that's what a Bayesian network here gives you. I mean, that's a great question, right? I mean, that's exactly leading into my new point. You look at this, and I ask you, maybe we'll just start. I ask you this question. What do you see here? This is gestational diabetes. What do you see? What can you interpret just by looking at this?
different elements which are but interconnected with each other.
Right. But let's just focus on gestational diabetes, and I ask you this question. What can you infer from this figure?
Influenced by 3 other parameters.
They are influenced by 3 other, we don't call it parameters, we call it features, right, in machine learning. So we can say in medicine they call it risk factors. Okay? So there are 3 risk factors that directly influence gestational diabetes. So easy. You don't know a Bayesian network, I am hoping. You do not know the semantic interpretation of this, but I give you this figure, you have an idea. Anybody else has a slightly different interpretation of this? So, beautiful. That was what I was going for. When I heard this, I did not hear anybody exactly say BMI causes gestational diabetes. Turns out that here is the cool thing. Every causal model can be represented using Bayesian network, but not every Bayesnet is causal. So you have to be careful, which is why I chose the word very carefully. I said BMI, age and race influence GDM, gestational diabetes. So I am not saying they cause diabetes, but if this is actually a causal model, then it is saying the exact same thing. BMI causes gestational diabetes. So let's make this clear. 9:43 on 3rd July, I am not teaching causal models. We are not learning causal models. So let's not think causal yet. We need a whole another tutorial on learning causal models. And people like Yudia Paul, who's you probably should know, the Nobel Prize winner in computer science, right? The Turing Award winner, who has dedicated his life to causality, essentially claims that you cannot learn causal models from observational data without interventions, without counterfactual reasoning. And so without doing all this, we cannot say that this Bayesian network is causal. So we use knowledge, sometimes it is causal knowledge, but because we don't do, this is a network that we learned, by the way, from our data. Because we learned from the data, this is not causal for us. The next set of projects that we are going to do is actually build causal models from this model. So to answer your question in short, if it is causal, you can read it exactly that way, but not every graphical model that you see is causal. So be very careful when we are doing it. Okay, but it's funny, in a machine learning setting, you call this the parent and you call this the child in the Bayesian networks. Then you think, well, that has to be causal, right? Parent is the parent of a child. There's a causal relationship, except it's just in terms of arrows and nothing else. So, do not think causal here. For the next 3 days, no causality, okay, even though I am talking a lot in medicines. So, what is this Bayesian networks? Well, let me see, I do not remember what I did. Okay. Let us just do this. How many of you knew the chain rule of probability? Anybody? Yeah. Hey, help me write this down. P of x1 given x2 x3, great. P of x2 given, beautiful, that is it, right. That is the chain rule of probability. I need to figure out how to get this down. Okay, that is the chain rule of probability, we know that. Now I give you some independence assumptions. Now I am going to say, well, let us just do this. How many parameters? Let us say that all x1, x2, oops, I don't know what's going on, x1, x2, x3 are, wait, what is going on? X1, what is happening? I don't know these technologies, man. I'm from a, we were just saying, I'm from a university that wants me to bring my own laptop to teach. So, any idea what is going wrong suddenly?
Touching the screen might be.
Okay, I'm not touching the screen. Okay, you know what? You're right. So, let's do this. X1 takes 2 values, or maybe it's this side of the screen. My machine learning tells me different things. X2 is 2 values, X3 is 2 values. So, what is the size of this table? What is the size of the table? How many entries in this table? Ugh, come on, faster. Madam, tea சீக்கிரம் ரெடி ஆகிடும் இல்லையா? ஏன்னா கொஞ்சம் எல்லாரும் எழுப்பணும். சப்ப கொஸ்டினுக்கு இவ்வளோ நேரம் யோசிச்சுட்டு இருக்காங்க. So, what is the size of this one? Number of independent parameters. Here is the key. I am asking you the question of independent parameters. Actually, turns out it is 8 minus 1, because if I give you 7, it is this side. If I give you 7, 0, 0, 0 to 1, 1, 0, 1, 1, 1 is simply 1 minus the sum over everything, this sum. Okay. So, the number of independent parameters is 7 here. With me? The chain rule of probability, what is the number of independent parameters here? Thank you, 1. If I tell you true, you can say the false. How about here? 2, right? Because if I say again, if I do this, this is 0, x2 is 0, 1, 0, 1. Well, if x1 is 0, then if I know this, I can get this as 1 minus p1, if this is p1. If this is p2, this is 1 minus p2. So, the number is 2. How about here? 4. So, that is 7. So, that is 7. Get it? That is your breakdown of chain rule of probability. Now, I tell you something slightly different. X1 is independent of x3 given x2, which means if I know x2, then knowing anything about x3 is not going to change my belief on x2, sorry, x1. What does that mean? If I have a table like this, I have x1, let's see that, let's say, how do I do this right? I think my hands are very fat for this one. Let's just do x2, 0, 1, then I am saying x3 is 0, 1, x3 is, no, let me do the other way. Okay. I need a 3-dimensional table. I have to do it in a 2-dimensional thing, right? So, this is x1 is 0 and 1 when x3 equals 0, and x1 is 0 and 1 when x3 equals 1. So, that is your 8, okay, here. Except if you look at this carefully and you say, well, if I know the value of x2, then the value of x3 does not matter, which means the value here p will be exactly the same as the value here. Okay, make sense? if this is 1 minus p, this is also going to be 1 minus p. Make sense? And same thing, if this is p1, this will also be p1, this will be 1 minus p1, this will be 1 minus p1. So now you see, instead of having 1, 2, 3, 4 that we had here, independent parameters, you are only having 2. So why? Because you are essentially saying probability of x1 given x2 x3 is the same as probability of x1 given x2. You have dropped x3 out of it. Now let us just take this and draw this as a graph. So I have x2 and I have x3, and my initial model chain rule of probability said x3 and x2 together influences x1. But now my domain knowledge or whatever data, whatever told me no, x3 is actually not influencing x1. So what will be your change in this figure? Remove the arrow, remove the edge. That's it. This is the idea of Bayesian networks. Okay. This is what Bayesian networks is all about. You start from this chain rule of probability, identify the independencies, the conditional independence assertions, and now compactly specify your joint distribution. Now what is the change? Now I am saying the following, you write it like this, x1 is independent of x3 given x2. Okay, I am going to say x2 is independent of x3. So what did my conditional, if I do the chain rule of probability, it had it like this, x3 was influencing x2 and x2 and x3 was influencing x1. This is how my first figure was. The moment I change it with these stuff here, this is going to generate a new figure, which is essentially saying x2 is the parent of x1 and x3 is sitting all alone by itself. Now how many parameters does this have? This has one parameter, this has one parameter, and this has two parameters. So how many total parameters? 4 as against 7 with just Boolean and 3 variables. Now you do this with 20 variables. You can see how much of a compact representation are you going to get. Now what is the advantage of going from 7 parameters to 4 parameters? Think learning. From a learning perspective, what is the advantage? You need less data. You need much less data to learn. Or going back to his question, you can trust the model more because it is simpler, it is easier to explain, it is probably more illustrative of this process. Make sense? That is the whole idea of Bayesian networks. I like to teach this from a very simplistic perspective. You start with the chain rule of probability, find independencies, draw the network, you are going to get a Bayesian network. Make sense? So let us go back. I know I made a mess here, but so what is the idea? The syntax is one node per variable. So classic machine learning, think of feature set, every feature will have a node. So this is your node, this is your edge. What is a Bayesian network? It is a directed acyclic graph. In computer science, DAGs, our favorite. It is a directed acyclic graph. If there is a link, it means there is a direct influence. It is not causal, it is a direct influence. It could be causal. I love it when it is causal, but it is not causal. In the general case, it is just an influence. A influences B. So the key is associated with each node is a conditional probability distribution, which gives the probability of that node given the parents of that node. What are the parents of that node? So now if I write out the full join distribution over all the variables x1 dot xn is simply the product of xi given variance of xi. Now, the coolest thing is the moment you have this giant distribution, I can do anything I want. I can say, going back to the questions that we asked, you can ask this question, x1 is true, x2 is false, what is the most likely x3 value? Well, look at the distribution, I will give you the answer. If I can say x1, I don't know why this is doing, I am not touching anything as far as I know, but we can do this. I can say x1 is true, I do not know the value of x3, I do not know the value of x2, but I want to know what is the probability that x3 is false. Again, very easy if I have the joint distribution. You just look into it, add things out, you will get the answer. So, the point I am trying to make is, if you learn a set of conditional distributions, you can compute the joint effectively. And your name? Srikant. Like Mr. Srikant said, the biggest advantage here is that you can interpret the model. If I look at this model, there is an interpretation for this model, and I can ask this question. Look, I know I have seen a woman, the woman has never smoked, her BMI seems to be reasonable, she is in her early 30s, okay, she is well educated with at least an undergraduate degree. I do not know about her prior history, we do not know about her family history, she does not know if her mom had gestational diabetes. What is the probability that she is going to have gestational diabetes? Let us say her race is also mixed. What is the probability that she has gestational diabetes? Boom, straightforward for us to answer this question. Some are missing, some are observed, some I do not care. Here is the output. Okay. So, that is the idea of Bayesian network. Any idea, like any questions on the fundamentals, because we will quickly go higher and higher. So, I am just trying to it is a crash course on intro to probability. Yeah. Yeah, I will show you how. I will show you how. Okay, we will definitely talk about that. How do these, where do these independencies come from? Turns out that you have, that is why Bayesian networks is very closely related to information theory. So, people who work in information theory can very easily jump into graphical models, because these independencies are completely born out of these information theoretic measures. Jan LeCun, right, so he always argues that energy functions are the way to go, right, that is his argument. I mean, he was a speaker at AAAI when we were there at AAAI, I was the chair of the conference, we are in the same table, we had a big fight, because I was like, oh, likelihoods are functions, probabilistic functions are cool, and he goes, energies are great, and there was this other guy, Christian Kirsting, who was like, why are you both arguing, one can be transformed to another. Yes, under some restrictions, you can do that, but not always, right. So, it's the point I am trying to make is that how you do it, there are many methods of doing it. I will show you some, but if you are really interested, reach out to Sahil or I or Saurabh, and we can give you some pointers as well. Okay. So, what is a Bayesian network? A belief Bayesian, sometimes called as belief network, okay, because it answers beliefs, right. Remember, this is the beauty about probability. Why do I like probabilities? Because it gives me an alibi. Sriraam, you told me that this I am going to win $1 million if I make this move. I lost $20,000. I said you will win $1 million with 0.98 probability, which means with 0.02 probability you would have failed, and just bad luck, it just came now. That is my alibi all the time, because I do not have to commit to an answer, I can always give a probability distribution and it is a soft answer. Why? Because that is a belief. The fact that it is a belief means it is not 100% true, it's you have a distribution over it. So, that is why Bayesian networks are sometimes called as belief networks, but some people would like to make it very explicit, they will call it a Bayesian belief network. Why is this Bayesian network? Do you guys, I have not explained that, right? Why is this called a Bayesian network? Any idea? Conditional probabilities, but what does that got to do anything with Bayesian? Bayes rule, thank you. What is Bayes rule? P of? Let us do A given B. Yes? Which is? Bring this to the other side. which is so what is it actually doing? It is just writing your factorizations in a meaningful way. That is why this network is called as a Bayesian network. Okay, it is very simple. It starts from base rule and it gives you a graphical notation for this base rule. Okay, again, what are the parents of a node? Parents of a node are the ones where the node directly depends. Okay, a belief network is a graphical representation of dependence and independence. This is the one key result that we will use. If I give you a network, you can read this network and say a variable is independent of its non-descendants given its parents. So, if I give you a network like this, right, we will call it 1, 2, 3, 4, 5, 6, then I can say 3 is independent of 5 and 6 if I know the value of these two. Once I know whether what is the value of 1 and value of 2, 3 is independent of 5 and 6. But because 3 directly influences 4, you cannot say they are independent. 3 if I change the value of 4, 3's value can change. Make sense? Yeah. No. So, the simplicity for anything that I am explaining, I am treating them as binary. That is a good question. It is general, I mean it can be discrete, it can be continuous, it can be anything, it can be mixed. Okay? In the end you need distributions. The distributions are over either discrete variable or continuous variables, right, and it is conditioned on the others. So, yeah, thank you for bringing that up, it is an important question. Yeah. When we do not know the value of 1 and 2, 3 is not independent of anything, because I do not know the value of 2, but I change the value of 6. Changing the value of 6 will change the value of 5, which will change the value of 2, thereby influencing 3. So, think of it as rolling a ball. Okay? If you roll the ball through this in the arrow directions, then what happens is that this can get affected. So, it is like a pipe and you have to block it. Okay? So, this is kind of like what it is, right. So, let us say that I am looking at a network and then I can say the conditional independence assertions can come out of it. So, for instance, whether this is the weather of the the place that you are in, and let us say you have a cavity, toothache or catch, and now you are basically asking from this what can I infer? You simply say weather is independent of everything. Weather does not seem to affect anything and nothing seems to affect the weather, but cavity and toothache, catch, they are all dependent. How? Toothache and cavity are independent, sorry, toothache and catch are independent if I know the cavity. Now, Sriraam wants to flip the story a little bit. Let us think a little causally here. Okay, I have a cavity. What can the cavity do? It is going to give you a pain. It sometimes can cause catch. Your things, it can just catch the side. Now, the question is, if I know that you have cavity, let us say the doctor sees that you have cavity, and then you go tell the doctor, I have a lot of tooth pain. What will the doctor say? Of course, I just saw your image, you have a cavity. Now you say, but there is also sometimes, doctor, it gets cut, like it is just a catch, I can't open it. Doctor says, I know you have a cavity. What does that mean? The doctor's belief on catch does not change because you said you have a tooth pain. Why? Because he or she already knows you have cavity. Let us say you do not know that cavity is there. The doctor has not done the image yet, they have not looked at your toothache. They are asking what is going on. Yeah, I have a tooth pain sometimes. Okay, then they may ask you this question, do you also have a catch every now and then? Because that will change your distribution on what is the probability of having a cavity. Make sense? So, that is the way they think about it. This is how medical diagnosis is done. Let us move away from catch and cavity. Let us just say that let us go for another one, right. So, let us say there is fever body ache, right, and let us say there is fatigue, and now you have flu, there is COVID. You go tell the doctor, I have taken a COVID test and it turns positive. I had fever, my body aches, I am tired. The doctor says, oh, let us also do a flu test. Will a doctor ever say that? No, they will immediately eliminate flu. There is nothing in the medical literature that says that you cannot have both at the same time. God forbid you shouldn't. As one of my friend had both at the same time, he was knocked out for 4 or 5 weeks. This is a very healthy 37-year-old male who runs marathons for fun, right, and he was knocked out for 5 weeks. We had both at the same time, exact same time. So, but the point is that the doctors will eliminate one. You have taken one test, I don't need another test. How do they do this? Via independencies. Now, they did the COVID test, they are not going to ask you, did you have fever? Did you have body ache? Did you vomit? Did you have diarrhea? Nobody cares. We know what the diagnosis is, so let us go for the solution. But let us say if they do not have COVID, they are out of COVID tests. What would they do? They are going to ask you all the questions, because they will figure out what is the most likely outcome in that case. So, this is what Bayesian networks is all about. If I can identify the one that influences it and set its value, then my belief on one does not change the other. On the other hand, if I do not have any means to do this test, or if this test is expensive, I twisted my ankle 3 weeks back, 4 weeks back playing pickleball. I went to the doctor, X-ray was immediately ordered, nothing on X-ray, but we do not know if there is a soft tissue damage. I had two choices, pay $2,000 out of my pocket and get an MRI, or live through the pain, figure out things later. What do you think I would have done? I am a poorly paid professor, man. Live through the pain. Live through the pain. Because I am coming to India. If something goes wrong, I will check there. I know the language better. But the point I am trying to make is that if this test was available, they would have done it. In US, insurance decides who has to live and who has to die. Okay? Insurance decides how much pain I have. Doctors cannot decide, the insurance will decide. So, unless we actually figure out whether this test can be performed, they are going to look at, this is the observations that they have, this is the underlying cause, the disease, these are the conditions, the observations. They are going to figure out whether there is a soft tissue damage based on how long it takes for my swelling to heal. Does that make sense? So, that is what Bayesian networks are all about. Instead of doing this in a guesswork fashion, you draw a network, then the network will tell you these independencies. Then we go back to your question. What is your first name? Mohit. Rohit. No Sharma. No, I am just asking. I became a new fan of Rohit as of Saturday night. But like Rohit said, how do you know that these independencies exist? Does it mean that you draw the network and then say, okay, that is how it is, or does it mean that you are going to learn this completely from data? The answer for me is it is hybrid, it is both. Some come from the domain knowledge, write your network as a function of the domain knowledge. Some comes from the data, which allows you to change your model as you go through. So, the way I always try to do these things is, I start by drawing an initial network. I tell the doctor, I need 2 hours of your time. We sit down, talk about the problem, we select the features, we draw a network. I will take the data, figure out how much of the network is valid, how much of the things need to change, and I will show you some operations on what those changes are going to be. We will do independence tests to see if this is true given the data. Then you will generate a new network that you can test in new data set. Make sense? Okay, so an example, if you have seen this example, again, if you really need a good book on this, I am writing this out. I do not know if, will this be saved along with the annotations? I think, okay, so yeah, this is one of the beautiful, beautiful, beautiful book. Have you read this, Sahil? Sahil? You have to, otherwise you are not graduating. I will give as a gift to you. Udia Paul has written a beautiful book in 1989, Probabilistic Reasoning in Intelligent Systems. Amazing book, amazing book. It kind of lays out this entire world out for you, explains this in a beautiful fashion. The theory is still relevant today. The follow-up to this book was called Causality, where he took the directed graphical model and used that to draw these causal models out. They called SEM, structural equation models, and they showed how to do that right. Anyway, so let's just take a simple example. Okay, let's say that you are interested in the home security. We all do that now, right? All kinds of cameras. But back in the day, nothing. You had two neighbors. The neighbor on the left is John. The neighbor on the right is Mary. John and Mary call you sometimes. Okay, why do they call? Because there is either a burglary. Okay, there is a burglary that could happen. Earthquake could set an alarm. Okay, if there is a door, when the door opens, the alarm goes off. That's how I wake up most of the times, because my wife or kid opens the door, forgetting that I've set the alarm on, and it goes off. Okay, earthquake, because of the movement, can definitely cause a alarm. And then when the alarm sounds, maybe John and Mary are going to call you. Hey, I'm hearing an alarm at your house. Are you okay? Okay. Now, I'm going to think of this from a causal perspective. Again, you don't have to, but in a causal perspective, a burglar can set the alarm off. So first, what are the nodes here? What are the variables? Burglary, earthquake, alarm. John calls, Mary calls. Now let's draw the arrow. The causal knowledge tells me the burglar can set the alarm off. What is the arrow? B to A. Earthquake can set the alarm off. Alarm can cause Mary to call, John to call. That's it. That's your causal knowledge written here. Now what do you do with data? Sorry, louder. You will learn the probability distributions. You will learn conditional distributions. But what if this knowledge is not there? You can learn them as well. That's what I'm going to teach you today, is how are we learning this from data. Okay. So as an example, we had the same network. The probability of burglary, maybe you are in a safe neighborhood, is 1 in 1,000. But on the other hand, you are in San Francisco, which means that every 3 years you have at least 2 earthquakes, pretty reasonable earthquakes. And when both of them happen, alarm goes off with 95% chance. When burglary happens, 94%. When earthquake happens, there's a 30% chance. When nothing happens, alarm just goes off sometimes, once in 3 years. And John is more responsive to alarm, but Mary likes to gossip more. So she doesn't call when the alarm rings as much as John does. I don't know. That's your network that you have learnt. Okay, but again, right? Remember what I told you about the compactness. If you have a Boolean variable with k Boolean parents, you have 2 raised to k rows, right? So if you think of 5 network, right? How many parameters are there? What is the size of the joint distribution? 2 raised to, which is, but there is, if I ask you for independent, -1, 31 parameters, right, which is exactly what you have. Okay. Now if you think of what is the size of this distribution, well, there is only one node here, one parameter, independent parameter here, because if I tell you the probability of true, burglary true, false can be obtained, right, as you can see here. Right, this is burglary, this is alarm equals true, alarm equals false is just 1 minus that. So 0.6 here, sorry, 0.5 here, 0.06, 0.05, 0.71 and 0.999, right, you get that. So how many parameters are here? 1, 2, 6, 8, 10. So you need 10 parameters as against 31 parameters. So what you are learning is a compact representation of the joint distribution. With me? I am hoping I am convincing you that this is a good way to learn. Okay. So what is the joint distribution? I again showed this many times. I am doing this very slowly. The first 1.5 hours is very slow on purpose, because next we are going to take off right after the break. So I want to do this slowly so you get the fundamentals. So the full joint distribution is simply the product of the conditional distributions. You can write this out, you will get the final probability. So what is the key? How do you generate these networks? Maybe that was Rohit's question. Easiest way to do that is I will give you an ordering of variables. In some sense, this is where causality becomes important here. Sometimes you know that there is this causal link that happens. Like you cannot say that gestational diabetes will cause age. Makes no sense, right? So you have some idea that some variables are come before than the other. So this in some sense is a partial order. Somebody gives you a partial order. So go through each variable, add that variable to the network. Now you figure out what are the parents of that variable. How do you do that? You essentially compute the conditional distribution of that variable given the parents and that variable given everything, figure out if there is independencies. If knowing the value of those parents renders this variable independent of all the other variables, then those variables are my parents. Okay, do that, and this choice of parents will guarantee that what you get in the end is a true joint distribution. Let us do one example before we take a break. Okay, a simple example. Somebody gave you the wrong order, but it is an order that Mary, John, alarm, burglary and earthquake. Okay, so now we are going to say, okay, first is Mary, then John. So I know that there is no parent for Mary because Mary comes first, no parent. Okay, then John comes. Then I am going to ask, is probability of John given Mary the same as probability of John? Well, that you can compute from data because it is just counting, right? If I give you out of 10 times that Mary called, John called 5 times. What is the probability that John will call when Mary calls? 0.5, 5 divided by 10. So it is just counting in the data. So you can do this and you can ask this question. Let us say the answer is no. So this means that there is a dependency between Mary and John. So you have to draw this. This is going to cause this arrow. Now I am going to say, okay, now that I have done with Mary, John, I am going to look at alarm and I am going to ask multiple questions. If knowing the John and Mary, is it same as knowing only John? And is knowing John and Mary is the same as knowing only alarm? That is, does alarm depend on Mary given John? That is the question you are asking. Now let us say the answer for both of them is no. Then that means this, the fact that alarm given John and Mary is not the same as John makes me draw this and this. Okay, make sense? I have to have both of them. Now I am going to look at this burglary given alarm John and Mary, because I finished this, I finished this, I finished this, I come to 4. Is it the same as probability of burglary given alarm? Let us say if that is a S, then I do not have to draw these arrows do not have to exist. Okay, I only draw this arrow, that is what comes from this, sorry, yeah, that is what comes from this. Now I am also going to check, well, do I even need this arrow? So I am going to check the next one, burglary given alarm John and Mary, is it just simply the probability of burglary? That is burglary just out there like weather, not influencing anything or not influenced by anything? And let us say the answer is no, so you are going to have that, and then you are going to continue doing this and you are going to get this network. Now I ask you this question, is this correct network? Yes or no? Yes, it came from the data, but not what we imagined. Why is it wrong? Nobody is talking causality here. That is the first rule I want to bring into your head. What is the joint distribution out of this? Write the joint distribution for this. The joint distribution for this is probability of Mary, John, burglary, alarm, earthquake. What is the joint distribution of the other one? Also exactly the same. So what am I doing? I am just reordering the distributions. So this is also correct. In the end, this is also a correct network. How do you know one network is better than the other? This is where you look at the number of parameters, you look at this thing. So what you do is you say, like you score a deep model, you can have a score. The score has two components. One is the likelihood given the data, and I will talk about all this, given data, and you, what is it you don't like in this that you like in this? Fewer connections. This somehow seems more, I don't know, cleaner. It's more easy to interpret. So that is your model complexity. The less complex, better it is preferred. Make sense? Okay, so we will take the break now. Do we have tea or yet? Okay, so we'll take the break now, and then we'll come back at 10:45, and we'll continue at 10:45. Yeah, so okay, we can start, I think. So again, right, remember Bayesian networks are directed, which means that you have a conditional influence, right? So you basically say, if I say P of A given B, then you have this interpretation. This is Bayesian network. On the other hand, if I give you just P of A B and I ask you, I want P of A given B, what would you do? You would simply divide by P of B. So in that case, if I just give you a network that does not have any arrow, it still works. So what is that that's good about this, that's not so good about this? You have an interpretation. You have an interpretation of an influence. A influences B. There is a deeper understanding of that influence. What is the advantage of this over this? In the end, the direction quite does not matter, because no matter what, this is the computation I do it. In the end, the computation graph that I need out of this is simply an undirected model, because you are talking of distributions at the end, and distributions by themselves are undirected. They are conditional, yes, does not mean they are directed. Okay. So what is happening is that when you have a probability of query given evidence, you are essentially constructing an undirected model. You are doing this and getting out of it. What does that mean? Let us look at this. Okay. Now I want you to do this. P of C equals, let us say, I keep forgetting that I can do this quickly. P of C equals true given A equals false. I want to compute this. But you do not have the distribution. You do not have this C given A distribution. What do you have? You have P of A, P of, and so what do? You take the product of these two, what do you get? What do you get? No given. This is what you get. From this, what do you want to do? You want to do what is called summing out B. You will say, I do not care about B, which means whether it is B is true or false, I do not care. Sum out their values from this distribution and give me the final distribution. Right? That is it. In the end, this is all that matters. Why? Because what is this, right? Again, I am doing this slowly, so you get the idea. It is essentially, I have A, B, C 0, 0, 0 to 1, 1, 1, and then I am going to have the probability. What am I saying? I want to know C is true when A is false. Let us do that. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1 1 0 and then you have 1 1 1. Great. What do I want? I want the case when C is 1 and A is 0. Now that is this one right here and this one right here. These are the two cases where C is 1 when A is 0. You want to do the probabilities. What do? Add these two probabilities. Correct? Yes? That's your conditional probability. But what are you really doing? You don't care about whether B is 0 or 1. So what are you summing over? You are summing over the values of B to get that final probability. Make sense? But remember, the moment you go here into this table and write this out, this structure is lost. I don't care about this structure. For answering queries, I actually directly go for my distributions. So you have to understand these two, right? So there is this idea back in 90s, people were arguing, I like directed models, I like undirected models. Can you think of a case where directed models are useful? I like this, the best examples. Directionality exists in time. What happened yesterday influences what happened today. What is going to happen tomorrow is not going to influence what happens today. That doesn't work that way. So if I want to model time faithfully, then I want to model it using directed models. How about undirected models? If one is time, the other has to be? One of you said that. Space. Spatial reasoning. So that's the exact way people used to use it. People who model temporal models used directed models. Computer vision folks loved this because it's just working with images, and images essentially are just spatial data, and you're working with spatial data. So this is what these were called as Bayesian networks. These were what are called as Markovian networks or Markov models. Both are mathematicians, as you know very well. So what is a Markov model? Markov model simply says there exists relationships, but then I don't care about the directionality. For instance, there is a relationship between smoking and cancer, and there is a relationship between having cancer, asthma and cough. I don't care which one is what. Okay, there is a relationship between smoking and cancer. There is a relationship between cancer, asthma and cough. So if I had to draw this, I would have probably drawn like this. Smoking causes cancer, and cancer might cause asthma, and asthma could cause cough. When you have cancer, you cough. This is my directed model for this undirected models equivalence, and I learn my conditional distributions. But there are some smarter people who said, I don't care this. Instead of learning these distributions separately, associated with each of them, I'm going to learn their relationship as just a simple potential function. It's a number. It is just a number between minus infinity and infinity. Higher the number, higher the stronger is the association. Very simple interpretation. Higher the number, higher is the interpretation. So smoking causes cancer. I'm going to give you a number. So the number of this is going to be 0.8. Okay, but the relationship between cancer, asthma and cough is 1.5. Now you quickly tell me which one is more possible in the world. Cancer causing cough or asthma is higher than smoking causes cancer. Make sense? So you can just read off this numbers. By the way, I made up these numbers. Don't go out and smoke and blame me. Okay, I am not saying please smoke. I'm saying the opposite, by the way. But the point is that this is just direct interpretation of the strength of the relationships. The other nice thing about these models is the independence influences. You can directly say smoking is independent of asthma and cough given cancer. Why? Because there is no link between smoking and asthma and cough. There is no parent, child, non-descendant, blah 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 nonsense. Direct. You look at this graph and you say there is no link, no relation. Done. So independencies are actually easier to read in this one. So why do I still like directed models? They give conditional influences. but they can represent causality. There is some advantage of doing that because I can get the causality in there if I want to, which is why I like them. I love graphical models, I love directed models because of the fact that I can establish some causality if I have enough knowledge and data and experiments. With these, there is no causality, there is just pixel level information. Each pixel is connected to its adjoint pixel. That's what you do, right? I mean, this is your Markov network. If I give you a 3D image, if I want to create a Markov network, that's it, right? This is your Markov random field. That's it. Each pixel is a node. It's connected to another pixel, and then you have some potential functions that explain how this is. So what do you get is a log linear model. So the probability of the configuration is simply the feature value that it takes and the weight that you have. Okay, in some sense, it's a log linear model of the potential functions. But here is the problem: this normalization constant is computing this is NP hat, because this requires going through all the variables of all the values, and that is over the entire space of possible features that you have. So you are looking at this entire example space to get that normalization constant. So what people do is all kinds of stuff, particularly in 1975, it's a beautiful paper by Besag, introducing this idea of pseudo likelihood, which also breaks this into a product of the individual potential functions, and then you are done. Okay, so you have to use some sort of approximations to train this. Make sense? So do I like these when I am doing spatial reasoning? But otherwise I am not a big fan, because of the fact that this part itself is so difficult to compute, whereas if here it's much easier because of the fact that these distributions are much simpler. I don't have to compute over everything, but just over things that I don't care about. Any questions? Okay. So independents are very easy. Two nodes in a Markov network are independent if every path between them is blocked. So if I look at this, if I set, oh, I know A is true and C is false, so I know their value. So once I know their value, I am shading them out, and now you find the pour the water through, it will block. So E is independent of B and D given A and E. In this case, actually given E. Okay, there is no path that takes me from E to B and D. B and D are not independent of each other because there is a direct link between them. Make sense? Any questions? Okay, so this is the easy interpretation, and from this you can do this idea of Hammersley-Clifford theorem. If the distribution is strictly positive and this graph encodes conditional dependencies, then the distribution is simply the products of clicks. So which means that you can do Gibbs sampling much more effectively on this, and I will show you how to do that when we do this. So what are Markov networks? It's simply the product of the potential functions that we have. In Bayesian networks, the joint distribution is simply the product of the probability conditional distributions. The potentials can be arbitrary number, as I said, between minus infinity and infinity. These are probabilities, so it's 0, 1. Okay, cycles are of course allowed, and cycles are cardinal sin in Bayesian networks. You cannot have cycles. Partition function is an annoyance because you have to do this global over all the variables of all the values. Here you are only doing it locally, it's a normalization. So as long as your conditional probability distribution sums to 1, you are fine. Independence check is graph separation. This requires a little bit more details on independence. I can send you papers if you want to, it's very easy. And inference, typically belief propagation or some sampling methods work very well. Ideally you will convert this directed model to an undirected model and do this inference, and I will explain some of those methods later. So what can we do? So we are by now we have established how to construct these networks. Okay, let's still do only Bayesian networks. We don't have to spend time on Markov networks. Okay, with me everyone on how to construct Bayesian networks. So what can we do? We can do what are called simple queries, right? So I can say, look, I am driving a car, but the gauge shows that the fuel gauge shows that it's empty, the lights are on, the car is not starting. What is the probability there is no fuel in my car? This is a simple query, because here I am basically, if I have 100 things in the car, I am summing out the rest 97 sum over the 97 things and only focus on these 3 things to answer the question whether there is gas in the car or not. Okay. And now I can also do conjunctive queries. You can say what is the probability that there is no gas in my car and I don't know, my carburetor is broken, given that it doesn't start. So you can ask this multiple times. What is the probability that the woman is a high risk for gestational diabetes and the kid is at a high risk of preterm birth, given that the woman is overweight, has never exercised, is smoking and still drinks alcohol. Now given that, you are going to ask this question. Now I can answer multiple queries together. I don't have to construct one deep model every time. It's just one graphical model that I can work with. Then I can also do things like optimal decisions. Okay, this I kind of referred to this yesterday in my talk. You can essentially ask this question: what is the correct action to take given that this is my set of observations? What should be my intervention? What tablet should I give to this kid given that the kid has high fever but doesn't show any other signs of infection? So you can do these kinds of optimal decision making as well. The other cool thing that we can do, and this is a problem that we quite looked at a lot in early 2000s, was what should we gather next? What information should we collect next? You go to a doctor, the doctor says do this test, you do a blood test, you come back, oh I don't see anything in this, but then there is some infection, do the next test, let's check your thyroid levels, let's test that. So they are going one after the other. So you can ask this question, why not do all this earlier? Well, because first it's A, wastage of resources, B, if it's a simple infection, why would I go all the way to that, put you through this, do upper endoscopy, that, this, MRI, why? Well, go one by one, eliminate one by one, that is what we do as humans. How can a machine do that? But most importantly, you have to answer what evidence should I seek next given that I want to maximize some utility, right? And so for instance, I was talking to Rohit and basically asking this question of, if I have an image of something, and let us say a non-destructive testing image, what area of this pipe should I image next given that I found a crack here? I think that is a very important question, a practical question there. But to answer that, you are asking not just what is the conditional probability of a query, but you are asking what is the area in which if I probe would I get the maximum value. Okay. Sensitivity analysis, which probability values are most crucial, because having maybe a flu is not as bad as having the chance of a heart attack, which probability becomes more important. Okay. And of course goes back to the question of explanations, what happens when I do A versus B? You can answer these questions. Okay. Okay, how do we do this? Simply we do this by enumeration. Let us say a simple query on the burglary earthquake. So let us say that John has called and Mary has called. So I got call both from John and Mary saying the alarm goes off. Now what is the probability that burglary could happen? Let us say I have 2 missed calls. Forget that they told me that the alarm has gone off, that is a different story. Now in this thing there are 2 missed calls, one is from John and the other is from Mary. What is the probability there is burglary in the house? Very simple. So I am interested in probability of burglary given John and Mary, which means if I write this out, if do the base rule, I am having the joint distribution over probability of John and Mary along with burglary divided by probability of John and Mary. We will take this is a constant alpha, a normalization constant. So that alpha times P of B j m, but I do not have the probability of B j and m, I have the probability of B E a j m. But then I realize I do not care about these two, so I will move them to the sum. I will sum out E, I will sum out A, and then I look at the joint distribution. That will be my inference problem. Okay? I see a lot of you nodding your head, so you are with me. So, but now what does this mean? Write this out. Again, this is probability of B and then probability of E. This is simply probability of B, probability of E, probability of A given B E, probability of J given M, and M given A. See how B is in caps, everything else in small. Any guesses why? Because B is the query. I hate this. Sorry. Because B is my query, these two are my evidence. and the small letter means values. Because I'm summing over them, in one case A equals true and the other case A equals false. E equals true, A equals false. But now I look at this expression right here and I realize, well, this is B doesn't even depend on E, right, and J given A and M given A doesn't depend on E. Why do I do this way? So what do? I rewrite this. I rewrite this such that the dependencies are coming out. So alpha times P of B, then I sum out E and then I say probability of E and then I sum out A given B E and J given A and M given A. Make sense? This can be done using any search tree, particularly people do depth first implementation very fast. So this is how you answer any queries. Turns out that as in life, it's not easy, it is NP hard, in fact it's P-space complete. So you resort to other types of inference techniques. Sampling and belief propagation are most common for this one. But in enumeration, essentially you write the whole thing out. I am not going to go through the algorithm. You can go to Russell and Norvig for this enumeration algorithm, but the evaluation tree is what will give you an answer. Okay. So what am I doing? First I am going to sum over E. First I have the probability of B, so I write that out here. Then I am going to sum over E, and then I am going to say probability of E, which means E is going to be true or E is going to be false. So that is going to be this branch here. Then I am going to say probability of sum over A, probability of A given B. So sum over A means A is going to be true or false, but I have to do this for every E. So when E is true, A can be true or false. When E is false, A can be true or false. Make sense? And then you say J given A, M given A, J given not A, M given A, and you see this. Make sense with me? This is the evaluation tree. Is this efficient? Why? Why not? Yeah, you're sorry? There's too many variables, this is not going to be feasible, but still you will get the tree. But just look at this particular tree. You will do all the combinations, but you have to do the combinations anyway. Are there any repetitions? What can you do? Well, the factorization is done, but what can you do? Cache, yes, store it. Compute it once, store, and then use it again. That is the idea of variable elimination. Okay, you just like factorize is the right. It's called constructing a factor, but the idea is storing it. You store the intermediate computation as what you call as a factor. Maybe that's what you are going for. The intermediate computation you will store as something called as a factor. Factor is the intermediate computation. So instead of doing this repeatedly, what you will do is write this equation out, and then you say I am going to compute this, that will be the factor of Mary, and then I am going to compute the factor of John. Then I do not have to do this multiple times. I have the factor of John here and Mary here, and then I have, maybe I will call it John. I mean, this is actually the same factor, it is just two values depending on how you do it. So you will store it and then you will retrieve it, and then you will sum over A, you will construct a factor for A. So again you go here, right, this is the same, this is not the same, but you can see that it is still splitting on A. So if I store it, maybe in another tree I might need this, so I will store it once. So the idea with variable elimination is you store these intermediate results and then you can retrieve them later as you go through. So you will avoid computation, expensive computations. Another example is a large tree like this, and what am I interested in? I am going to query D given H. I mean, we are taking the most difficult cases, right? D is somewhere in the middle, H is at the end. So I am interested in the probability of D given H. H is the small h, so just taking the value small h. Okay, what do you do? First you take these two, eliminate A, you get the factor for B. Then you take C, D given BC, EC, these are the things that contain C, eliminate C. What does eliminate C means? Sum over A, sum over C. You get the factor of BDE. Now you get here, and then you have the observation. So this is a factor of G, this is an observation, eliminate I, you will get a factor of G. There are two factors. One factor of G comes from the because it influences the evidence, the other factor is because it influences something that is hidden. So you will get one factor F3 from here and F4 from here, and then you multiply all of them, you get the final result. Make sense? So you just store, compute, store, compute, store, compute, store, compute, store, and keep going until you finish. But there are a lot of APIs that already do this for you for free. You can do this very easily. Just give the network, ask a question, you will get the answer. Except, as I said, if you have tree structures, singly connected networks or polytrees, you are essentially polynomial. But then if you have very large trees, this is exactly the same as three satisfaction problem. So it is NP hard, and you can actually show that this is equivalent to the harder problem, which is counting in three sat problems, which is hash p complete. So this is a very expensive approach if you are doing it exactly. So let me see. Oh, I am directly going to learning. I am not talking about the other methods. So what are the other methods? One method is called as. Do we have slides on that? Do you know? Sampling. Do we have slides? Did I remove them from the last? Okay. So you can do sampling. So what does that mean? If I go here, I know the distributions, right? I know the distributions. So what I can do is I can simply do multiple types of sampling, right? So here I know the distribution. I flip a coin, and the coin could say that A equals, let's say, false. So what I'll do is A is false. Okay. Maybe I'll construct a table. So A, B, C, D, all the way till I. Okay. So I'll say A is false, and then now I'm hold A is false. Now I have a table here which gives that when A equals false, B is true and false. So you have a distribution there. I sample. What is sample here? Throw a coin. Okay. If this is 0.6 and this is 0.4, you flip a coin, right, or generate a random number. If the random number is greater than 0.6, you assign this as false. If the random number is less than 0.6, you call it true, right. So maybe the random number comes as 0.4, so I am going to make this true. Now hold B and generate D. Hold D and hold B and D, generate C. So you can do this multiple times. You will fill the data table. Now in this table, look at the number of times H is true and compute the times that D is true. That is your final answer. This is a typical sampling method. This what I am doing right now is called as rejection sampling, because in this case when H is false, I will throw that sample out. I will only hold the cases where H is true. That is rejection sampling. You can have importance sampling, where you can calculate the weight of each sample based on the joint probability distribution, and then the final result is simply sum of those weights. You can do Markov chain Monte Carlo, where you can essentially generate one data point. Now hold all the variables in that one data point, change only one of them for the next one. So you generate data points where you just change one variable at a time. That is called Markov chain Monte Carlo. And MCMC, there's GIP sampling, there's many sampling methods that one can do in Bayesian networks. I am not going into the detail of all this because it's a 6 months course, okay, but I can answer questions if you have any. So this is how you do inference in Bayesian networks. And we are going to now start talking about learning. Learning is straightforward. If I give you A and I ask you how many times is A is true, I give you a data set, what will you do? Let us say A here is gestational diabetes. So I give you a data set of the pregnant women, Garbini. We have 6,000 women in this data set. I want to know what is the probability of GDM, gestational diabetes, is true. What will you do? Somebody count what? Count the number of times gestational diabetes is true divided by 6,000 total number of women, right. Now I said I changed the question. What is the probability that gestational diabetes is true? Equals true given age is greater than 35. What do you do? Eliminate all the records with age less than 35. It seems like an elimination guy. I like him. I would just select the records with the age greater than 35, but elimination also works. It's potato, it's the same thing, okay. But so what do? You count the number of times that age is greater than 35 and you count the number of times GDM is true given age is greater than 30 and age is greater than 35. So, in that after elimination of those data sets, in that small selected data set you have, count the number of times gestational diabetes is true. So, what you do is what is called as maximum likelihood estimation. That is the beauty of all these probabilistic models, because MLE in probabilistic models is simply fractional counts on the data set. So, what you do is you simply count the number of times something is true in the data set, and so you count the number of time parent is true and then count the number of time the child is true and the parent is true. That gives you the probability that the child is true given the parent is true. You can do this for anything. So, the cool thing is, I am hoping I am convincing you, if I give you a fully complete data set, nothing is missing, a fully complete data, I will keep this down, a fully complete data set with no missing data, and I give you the model, then learning is trivial. Somebody writes the model out, somebody gives you a beautiful data set, it is done. And I am always surprised why people do not use Bayesian networks, because they do not know about this, because you can actually learn a good model out of it. It can answer any arbitrary queries, you have good data. The real problem is when you have missing data. So, here for instance, I have told you this, right. So, you have this data set, we will do his elimination, this is all age less than 35. So, I am eliminating this, I am looking at this data, everybody has age is greater than 35, all the way to 45, let us say, and I have many data here, okay. Now, what happens if some data is missing? There are some cases where I do not have age. What can you do? Again, the technique for doing this is rather old, it is called EM, okay. The EM idea is very simple. If the data is complete, you count one iteration across your data set, you are done, zoop, done. If missing value, what do we do, right? So, you do what is called as expectation maximization, but before that, what are the alternatives that you can do? One is, I can say here, I can basically say, well, looks at this and I look at this data of the age and I will say, what can I do? I will probably get the most common age and put that in. That is a guess, you are guessing that to be the most common age from your data. You can also say, this is the average age of the population, I am going to insert that one in, which is one is median, the other one is mean. You can also do, I am going to find a woman who is closest to this particular woman in everything else, and then I am going to absorb her age. Again, a reasonable thing to do. So, there are many such techniques that exist, okay, most probable one, the average value and so on. And what can you do? Then you can do the counting based on that and you can iterate. I am going to change the strategy, keep going until you get a good estimator. But the better way to do that is the idea of incomplete data. Now, let us say this is my current model, okay, I have, this is my network, there are only two variables A and B. A, and I am starting with no domain knowledge, so nobody tells me anything. So, I am going to assume uniform distribution, which means A is true with a 50-50 chance and B is true if A is true with a 50% chance, B is true when A is false also with a 50% chance. So, it is completely uninformed prior distributions, that is where you are starting, make sense? Okay. So, now I am looking at the data. In the data there are, when A is true, B is true, when A is true I do not know the value of B, false true, true false, false I do not know the value of B. What could be the values? Can you fill in? false, false, false. Why? It's because you don't have the data. I want the data, but it's not here. You know what you are called then? You are called as a TV network. They will got their results the way they want to. They will tell you that result, and they want you to believe that is the truth. US elections are going on right now. Whew. See, in India, when we have elections once in 5 years, the election commission typically announces the election like 4 months in advance. For 3 months there is election fever. In US we have elections pretty much every month. Why? Because there is a every 4 years we have the president election. Every 2 years we have the house election. That's the equivalent of Lok Sabha here. You have elections every 2 years for the house. Every 6 years for the Senate. So 2, 4, 6. And then there are local elections. So we are always in election mode. So if I switch on a TV news channel, there is no news. There is only bias. So if you put false, false, that is your bias. Because you want to see that. It's not there. Insert it. 5 rupees. Put it in. That is the bias. We should not do that. So what can you do? False, true. Why? Because that's what I saw in the other data. You know what that is called? Memorization. How we do our 12th standard here. Get everything in, go spit it out, done. Can we do differentiation? How many master students from India, when they come to US, I ask them to simply differentiate an exponential function, which by the way is just an exponential function. They can do it. But they would have got 200 out of 200 in their math, in their 12th grade. Why? Because you memorize it, you spit it out. So that is also bad. So what do? I don't want to do what she says, which is create a good data so that it is fair, everybody is represented. No, that's not real world. I can't do what he wants, which is memorize and spit. So there has to be something in between. You compute these expected values. What is the most probable values? How can we get the most probable model? Okay, so that's what we're going to do now. So the idea is very simple. So let's do it this way. What I'm going to do is, given my current model, now current model says probability that B is true given A is true is 0.5, okay, which means with a 50% chance B is going to be true here. B is true with 50% chance here, okay, true with 50%, 0.5, 0.5. Same thing here. A is true, this is going to be B is true with 0.5, 0.5, okay. But now I am going to count. When A is true, B is true. How many times? You get 1 out of this count, and then you get a half from here. So you get a weight of 1.5. A is true, B is false. How many times? You have 1 here and 0.5 there. So that's also 1.5. Now A is false, B is true. Again 1 here, 0.5 here. So that's 1.5. But we don't have false, false. We only get a 0.5 from here. So that will be my weight. Now these are the counts. These are the actual counts. Now let's turn them into probabilities. How can we do that? Again, you do the maximization. What is the probability of A is true? Well, that is easy. A is true in these two tables. So that's 3 divided by 3 plus 2, 5. So that's 0.6. What is the probability of B is true given A is true? B is true given A is true, that's 1.5. B is false given A is true, that's 1.5. So that's 0.5. What is the probability that B is true given A is false? Now this is where it gets interesting, because B is true given A is false is 0.5. B is false given A is false is, B is true given A is false is 1.5. B is false given A is false is 0.5. So this is 1.5 divided by 2, which is 0.75. So you see, you started with this as your distribution. Use this to compute the expected counts. So this is why it's called an expectation maximization. You compute the expectation here, and then you compute the maximum likelihood here. I got to this distribution from that distribution. Make sense? Should I stop? No. Why? Because this distribution and this distribution are different. So what should I do? I should bring them closer to each other. How do I do it? Iterate again. Go back and do this again. How do you, now if you do this, this is my new thing that I start with, and now I am going to say with this, let us fill in the data, right. This is my expected count. Again I have a different expected count. Now using this expected count, I will get new different data. Now you change, your distribution has changed, but you can see something, these two are still remaining the same, only one of them changes, which means you are getting closer to convergence, but you have not converged yet. But you continue, iterate, complete until you complete the learning process. Make sense? Okay, we will take our 2-minute break here before we finish the rest of the thing, and then you will take over tomorrow. I will come here too. Yeah.
How would this work for continuous distribution?
Continuous distributions, that is a great question. Again, what everything has an estimator, a sufficient statistic, estimate that and keep going. So if you are interested in a Gaussian, estimate the mean and variance and just keep going, and that is it. So it is exactly the same. We love discrete, 2 reasons. Discrete optimization is actually harder than continuous optimization. So if you can figure out how to do this right, the other one is easier to solve. But discrete is easier to understand for humans than continuous. So that is why we love to do it this way. But that is a great question, yeah, again good questions. So the cool thing about this method is that it can keep going and it can converge. Of course, does it converge to the global maximum? No, it always converges to the local maximum, but there are conditions under which it converges to global maximum, but very rarely. I would think that it is always a local maximum. So you just do random restarts, keep going until you converge. I think you had a question, yeah. Oh, yeah, I'll hold on to the end, I'll explain that. Any other questions before we continue? Unlike my classroom, nobody seems to take their phone out. And when I teach my class, there is that 40-minute, 37-minute mark. Right when I say you can take the 2-minute break, you will see that everybody will have their phone out. Because I have a rule, no laptop, no phone in my class. That is how I have been teaching for 15 years. No laptops. So first class that I taught, back then there was this thing called MySpace. This is in 2009. The head of the department was sitting behind in the last seat, and he came to me and he said, Sriraam, one student was checking MySpace. That is the first class that I taught. So from my second class itself, no laptops allowed. And it has now been 15 years. No laptops allowed, no phones allowed. If people take their laptop or phone, I will call them out by name. So they will, and then ask them a question which has nothing to do with this slide, but something like told 10 slides back. And then they will be like, after that nobody takes the phone out. But right when I say this, okay, let us take the break, then you will see that tap, 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 tap. You can actually hear the sound of those phones coming out. I teach a class of 120 students, so you can see that pop, 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 pop sound come out. So nobody is taking the phone, so let us continue. Okay, so here what did I assume? I assumed the following. I assumed that this is known. So in a Bayesian network, you have 2 things, right? You have the structure of the model, which basically tells you in some sense what is known in terms of the influences. Okay, so you know the influences, known influences. What is missing is the parameter, the conditional distributions. Okay, so that is why this is called as in Bayesian network terminology parameter learning. Okay, in parameter learning, the question is, where do numbers come from? Okay. So you have a known structure, unknown parameters. So you have data, known structure, unknown parameters. You do maximal likelihood estimation. I have known structure, unknown parameters, missing data, you do expectation maximization. But that assumes you know the structure. What happens if you do not know the structure? I do not know the structure of the Bayesian network. How can I learn it? How will you do it? Just guess. I am pretty sure your guess is so much better than mine from 22 years back. So go for it. You assume a structure and then do what? Somehow score that structure. Somehow you have the goodness of that structure, okay, and then you see how good is the new structure compared to the old structure, make some changes and old structure. So I like that idea. Start with an assumed structure and do what? You have to define some operations. What are the operations that you would do on that structure? How can you change a structure? By eliminating some edges. Our guys are very good at reduction and elimination all the time. Let's add some more edges, bring people in. No, eliminate, reduction. So our system, our society is very nice. I like it. Okay, elimination. Now we have to do addition. Is that it? No, add is addition. Elimination, addition. That's just one more operation. Updation, how? No, scores, no, that is not an operation. I am doing a graph operation. I want to operate on the graph. So the idea is very simple. Like he says, reduce the graph, which is remove an edge. Then he says add an edge. Great. No, updating weights is parameters. I want a structure on the graph, I want an operation. Let's do this. I have this. Okay. This is my initial structure, like he said. And then he wants me to eliminate an edge. Done. Now he wants me to add an edge. Done. Invert the edge, reverse the edge. Remember, I started with this as an assumption. I could instead have this edge. Is that more correct? And in each of them, like you all said, have a score. So locally you make a change. You make a change, score that network, see if this score is better than the previous score. If it is better, keep the new structure. If it is not, go back to the old structure and keep continuing. Very simple. Okay? There has to be a catch somewhere. What is the catch? The score. There's a lot of research inside what the score is. And then how to do this search over large structures in a reasonable fashion. But I will explain that a little later, right. So structure learning is very simple. If the data is complete, again this is the easy case, which no missing data. What you do is update the score after the local change and rescore family. So I could start from this network, okay, and then I can say I could add a edge, which is the edge from C to D, or I could reverse an edge from E to C, or I could delete this edge. Now I can say which of this 1, 2, 3 scores better than my 0, and use that. Whichever has the highest one, you use that. Sometimes you won't even do all 3, you will just pick one of the operations, do it, see if it improves. If it improves, go there and then make the next change and keep going until you converge. Sometimes some algorithms do all 3 at the same time. So it really depends on. So the research was basically how do you, what operation would you do next and how do you score. Many scoring functions, but typically the scoring functions is log likelihood minus model complexity. This is typically the idea, okay. And then there are some Bayesian scoring functions, which is computing the log likelihood times the prior of the model complexity. So this is the Bayesian scoring function. This is more like the information theoretic scoring functions, okay. Like so called BIC is the most popular one, Bayesian information criterion. And then there is the Akaike information criterion, AIC, and so when we do BIC, we realize that sometimes the model complexity is too strong. So in my PhD thesis, I came up with a different scoring function that I called as conditional Bayesian information, where I didn't look at the model complexity of the whole joint distribution, but instead on each of them separately. So if I just use log likelihood, what happens? Intuitively tell me this. So I have 3 variables, okay, and I can have multiple networks, okay. Maybe I'll have this network. One second. Right, you can have multiple networks like this. Which of this network do you think will have the highest log likelihood, which is essentially the product of parents of xi given pa of xi, which one do you think will have the highest log likelihood? The complete network. Why? Because it is the most complex one, which means it will fit the data the best. From a machine learning perspective, what is the problem? Overfitting. Thank you. You will easily overfit. So what does this model complexity do? It is a, exactly, it is your regularizer. So that's your trade-off. I have my model complexity, which will, as the higher the model complexity, so the most complex model is going to give you the best accuracy on the training set, but we know we cannot trust the training set. So you go for the model complexity. But the problem is, many of the model complexity, the regularizer is too strong. So you will start underfitting the data, which is what we showed in our thesis. In my thesis 18 years back, we showed that you will easily underfit if I directly use this. So I had to scale it down further, but I scaled it down in a heuristic manner. I wanted to graduate, I didn't have time to do a lot of theory, so I just did some heuristic scaling down. I wish I had done it right, but we did that and it worked better. So the point I am trying to make is that this was the research. So the research inside machine is still going on. Depending on the type of the networks, what is a good scoring function? What are the operators? How can you do this very effectively locally? Make sense? Now, did I see a hand here somewhere? Yeah. No, reversing is not the same as addition and deletion, because reversing is telling you I already have P of A given B, but now I want to estimate P of B given A. To achieve reversal, you have to delete and add, yes, but that is not the same in a from a network perspective. Okay. So we do, when the data is missing, you do what is called a structural EM. The idea is very simple to the parameter EM. So you have an initial model. This is my initial model. Like he said, just guess a network. That's your initial model. You have the training data. So what you do is you compute the expected counts. So what you have to do is first learn the parameters. So oops, sorry. I don't know, man, I hate this. First learn the parameters, right? So you learn all the thetas. Based on the theta, you will compute the expected counts here. Okay. Once you have the expected counts, you can score, and once you finish the scoring, you can change and go for that. Now, given the new one, you will get a new network, new expected counts, keep going until convergence. So it's really taking the same EM algorithm, combining it with the expectation maximization idea, combining it with search and score. How do you score and search and keep going until convergence? Okay, and that's the idea. Why is this annoying? Because, so remember, when I am doing structure learning, what do I have to do? I have to compute the score. What does the score need? The score needs log likelihood minus some penalty. What does the log likelihood need? The parameters. Okay. So when I do structure learning, inside every iteration of structure learning, I have to do parameter learning. If the data is missing, inside every iteration of parameter learning, I actually have to do inference. Remember, because I have to compute P of B given A. There it was easy, it was A and B. Now if I have C also, and I have A and B are missing, and I observe only C in the data, I actually have to compute P of A and B given C, which is probabilistic inference. Does it make sense? So if I have to do this, inference is inside, I have parameter learning outside, I have structure learning outside. What did I tell you about inference? This is a beast, because inference is NP hard, and you guys should hate me by now. 2.5 hours of convincing you this is a wonderful idea, we should do this. At the end I am telling you, dude, this is extremely complex. because the innermost problem is an atom bomb. It takes a lot of time to solve, right. So, that is really the problem. Inference is a issue, inference is NP complete or hash P complete in this case, and this is really the inner loop of pretty much everything, but that is the mystery, that is where he comes tomorrow. What we want to do is make this easier. How can we make this easier? So, historically, maybe that is going back to the question on belief propagation and sampling. Historically, what we did was we did one of the two ways. Okay. So, I am going to, do I have a, I need an empty slide, maybe I can do that. So, when I think of inference, right, in Bayesian network, there are many ways to do this. One is exact inference, and I showed you that. Variable elimination, there is something called as bucket elimination, and there is a whole bunch of algorithms that can do exact. And then I told you sampling, where we talked about how you can sample one value based on the other values and keep going and finally do the fractional counts. Then there is a third method that we call as deterministic approximations. What does this means? This means I can develop a type of a inference algorithm that is guaranteed to be provably correct under certain structures. So, if the structure of a Bayesian network is a tree, then it is a guarantee to give exact result, otherwise it is an approximation, but I cannot bound the approximation in the arbitrary case. Again, if you go back to the Pearl book from 1989, he talks about this idea called as belief propagation. The idea is very simple. You have a network like this, right. I am purposely not drawing, well, let us do this, maybe it is a tree for the initial case. Okay. Then what you do is, you will start sending messages. Each node will send its neighbor a message. Okay. It is kind of saying, this is my belief of where I am. So, it will tell you, right, I think I am positive with the 0.3, I am telling you, you will tell him, he will tell him, and he will keep going of your belief, local beliefs. We will keep sending messages back and forth till my message to you will not change and your message to me will not change. That is when we converge. Okay. Turns out that if you have this as a tree structured network, the messages will definitely converge to the exact probabilities. In the case where this is not a tree, let us say you have a cycle, right, like this, then actually they will not converge. In fact, they will go back and forth really bad. The smaller your cycle is, the more terrible your network is. So, what does that mean? If I have a, this has a cycle of 3 in some sense, but if this one, right, I could have something like this, blah 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 blah, and then this, that is a cycle there. Okay, this ends here, and then maybe I will have something that goes like that here. Now, this is a large cycle. Here BP is actually very close to the true output. So, it really depends on how you use belief propagation. Okay, it is a sending of messages. In some sense, we actually, if you look at our, this is, there is a paper by Ahmadi, Kirsting and myself, Natarajan, from 2009. We actually explain this with colors. It is called color propagation. So, you say if you are the query, you are blue color. If you are evidence, you are red color. Otherwise, you are green color. And you can just send colors back and forth. And at the end, if just figuring out where the colors converge, you can actually solve this problem. So, all the people who are in the evidence will belong to one category. All the people who are in the query will belong to other category. You can send these messages based on this color propagation, and you can show that it still converges in large graphs. So, that is really the idea of deterministic approximation. So, this is how inference was done. But then in 2000, from 2003, people have been saying, how about we make, so what is the problem with this? This is NP hard in general case. Okay, we know it is polynomial in trees. So, why not learn models that are much more tractable. So that is the key point of this workshop tomorrow. So day 2 is extremely important. What we are going to show you is, can we learn tractable yet expressive models? Okay, so that's what Sahil will walk you through that. The idea is very simple. You have already your deep learning models. You have your GANs, variational autoencoders, and of course now LLMs and stuff. And you have these deep learning things going on, and you have these probabilistic models that I just taught you today, Bayesian networks, Markov networks. You can have fully factorized distributions, simply nodes without any edges and so on. And then there is this intersection. And can we focus on that intersection? Right, and that's what the normalizing flows and variational autoencoders are in there, but there's also models that are, as I said, in the intersection here, but also closer to here, and we can work on these models together. And so this is the part that you are covering tomorrow, right, and you are covering in some sense this on Friday, correct? And so this is the theory that we are going to do tomorrow and day after. Okay. So I think with that we are done for today. If you have any other questions, feel free to ask me.